Thank you all for attending this online seminar to hear about Quintic Spectrahedra. And thank you to the organizers for having invited me. I'm very honored to be the speaker today. Today, I'm going to tell you about a project I did last year with Kashgali Koshesov at TU Braunschweig and Mario Kumar at TU Dresden. And I'm going to be telling you about mathematical objects called spectrahedra. In particular, we will look at three-dimensional spectrahedra, and specifically at quintic three-dimensional spectrahedra. And I'm going to present a classification theorem of these based on some combinatorial data we can pull from these objects. So this project was inspired by a much larger project on linear spaces of symmetric matrices, which occurred last year, online, but centered at MPI Leipzig, where I'm at right now. And it was coordinated by Orlando Marigliano, Mateusz Mechalik, Christian Ronstad, Tim Senaif, and Bernd Sternfels. And together, a large group of us answered a bunch of questions about linear spaces of symmetric matrices. And there's set to be a special issue in Les Mathématiques on these projects. You can find the paper that I'm talking about on the archive. There's the archive link or number right there. And so let's get started. Before I tell you all what a spectrahedron is, I want to tell you about a simpler object called a polyhedra. So the plural for this is polyhedra. And all they are is they are the intersection of a bunch of half spaces in some r to the n. So what you have presented on this slide is a polyhedron in three-dimensional space. And it is the intersection of 5 distinct half spaces, which I've described on the left by linear inequalities. And I've always moved everything so that the zeros on the right and everything on the left is greater than or equal to those things. So basically here, what I'm describing are triples of real numbers, x, y, and z, which are all non-negative. Their sum is less than or equal to 1. And the z coordinate has to be less than or equal to 1/2. And so there are many triples of numbers that satisfy these properties. And they're all displayed on the right. Okay, so here, this is the x coordinate, this is the y direction, and upwards is the z direction. And you get this object called a polyhedra. Now, polyhedra are interesting mathematical objects in their own right. You can spend a whole mathematical career studying these and still having more questions. They're very nice in that they can be described via all of this combinatorial data. You can ask how many vertices are on the polyhedron, how many edges, how many faces of a higher dimension, etc. So they're very combinatorial objects too. And as far as applications are concerned, they're extremely important for linear programs. A linear program is simply, the task of a linear program is simply to optimize some linear function over some subset of the real numbers, which are constrained by linear inequalities. So the real numbers constrained by these linear inequalities form exactly one of these polyhedra. And then optimizing a linear function means just finding the maximum face in one of the directions, for example. So for example, I might want to maximize the function 3x plus 2y plus z plus 3 over this polyhedron that I've drawn on the right. And that will give me some face of this. And these are very important when it comes to applications. They appear all over. And so the takeaway for this slide that I want you to remember after this talk is that polyhedra are exactly the feasible regions for optimization problems called linear programs. Moreover, we know a lot. We know a lot about polytopes. People have been studying polytopes for a while. And so they're fairly well understood, although there's always questions about whatever mathematical object you study. On the next slide, I'm going to write the same thing as I did on this slide, but in a funny way. So here again, I have my linear inequalities. And on the right, I have the geometry corresponding to those inequalities, this polyhedron. And instead of describing it via these linear inequalities, I'm going to describe it by asking a particular matrix is positive semidefinite. So a matrix is positive semidefinite when all of its eigenvalues are non-negative. And so what I do is for each one of these inequalities that I've written, I'm going to put the left-hand side as one of the diagonal entries. Okay, and that's what this matrix is here. It's a matrix A, which depends on X, Y, and Z. And then I'm just going to expand it like this. And so now I've described this matrix as an affine linear span of 4 symmetric matrices, because every diagonal matrix is symmetric. Okay? And this is all supposed to be suggestive of a definition that's coming up. In particular, this A0, A1, A2, and A3, they're just filled with a bunch of real numbers, and they're symmetric. That's their only condition. And now the question becomes, well, what happens if we let all of these matrices not just be diagonal real symmetric matrices, but any real symmetric matrix? And we ask for the same condition. We ask for the matrix to be positive semidefinite. What kind of object do we get? Do we get something that's convex? Do we get something that has all these flat faces? And so that's how I'm going to describe the definition of a spectrahedra. So like in the last slide, where I suggested that we let these be any d by d real symmetric matrices, we still look at this affine linear span of them. So this gives us a linear space of symmetric matrices. And we ask for which values of X, Y, and Z will this matrix have all non-negative eigenvalues. Okay, so I want all the triples of real numbers such that this matrix is positive semidefinite. This is called a degree D spectrahedron. And these degree D spectrahedra are parameterized by the data of 4 symmetric D by D matrices over the reals. And you can draw these, and here's what some of them look like. This is a spectrahedron of degree 3. So this comes from 3 by 3 symmetric matrices. This is a spectrahedron of degree 4. This is a spectrahedron of degree 5, which come from 5 by 5 symmetric matrices. And just like polytopes or polyhedra are the feasible sets of linear programs, these spectrahedra are also the feasible regions for some class of optimization problems. In this case, they're called semidefinite programs. And since, as we saw on the last slide, polyhedra are special cases of spectrahedra, a semidefinite program is a generalization of a linear program. And so there are many other optimization problems for which semidefinite programs can be applied. And again, all we're doing is asking to maximize or minimize some linear function over a spectrahedron. And so the next thing I want you to take away at the end of this talk is that spectrahedra are the feasible sets for semidefinite programs. However, we don't actually know nearly as much about spectrahedra as we do polyhedra. So we're interested in learning more about them. So the next thing I want to talk about is has to do a little bit with algebraic geometry. So if you've never seen an algebraic variety before, an algebraic variety it's just the solution set of a collection of polynomial equations. So for example, x squared plus y squared plus z squared minus 1 equals 0 is the sphere in 3 dimensions. And then we also allow for these solutions to be over the complex numbers. Okay, so we look at these varieties and their algebraic closure. And then the algebraic boundary of any set is just the smallest algebraic variety that contains the Euclidean boundary of that set. So for example, we have this polyhedron that we've seen before. And we look at the boundary. So this is the union of all of those facets, right? So nothing on the inside. It's like a hollow polyhedron. And we look at its algebraic closure. And that means that each of these facets has to live in a hyperplane. And so the algebraic boundary is the union of these 1, 2, 3, 4, 5 hyperplanes. Okay. Well, what happens when we do this with the spectrahedra? We get some wilder objects. They look very cool. They're fun to make pictures of. And these will be called symmetroids in the next slide. Okay, so symmetroids. So this algebraic boundary of spectrahedra. So the spectrahedra which we're going to consider are those that come from matrices, linear spaces of symmetric matrices like this, where we're just going to fix that first matrix to be the identity, which is totally an okay thing to do because after a linear change of coordinates, so long as there's some positive definite matrix in this linear space, you can always do a change of coordinates so that the first one's the identity. And that's going to make everything a bit simpler. And the algebraic boundary of this spectrahedron is called a symmetroid. And it looks like this. And it is an algebraic variety by definition. So it's a solution set to some polynomial system of polynomial equations. Well, what system of polynomial equations is it a solution set to? It's the solution set to setting the determinant of this matrix, which has entries which have very linear forms of a bunch of variables. It's when that determinant equals 0. Okay, so this is a surface in 3-dimensional space. It looks like this. And I want to draw your attention to these sharp points. You see all these singularities on it. And that's going to be very, very important for this talk. So there's a singularity there on the actual spectrahedron. Then there's a bunch of these singularities outside. Let's just do one simple example. So here I am in the case of d equals 3. So I'm looking at linear spaces of 3 by 3 symmetric matrices. And I've written one here, and I've written its determinant. So the spectrahedron is when all the eigenvalues of a specialization in this space of matrices are non-negative. Equivalently for symmetric matrices, I'm asking that all the principal minors are non-negative. So that translates to these inequalities, but that's not so important right now. The important thing is that we can plot the solutions to this determinant equation. And we get this determinantal hypersurface. And the thing I really want everybody to remember throughout this talk is that points on this space. So if I picked a point right in the middle of this samosa looking thing, that corresponds to a matrix. So points here are matrices. And if I'm on the inside of this convex body, this spectrahedron, then I'm a matrix with all positive eigenvalues. And now let's think about what happens as I try to leave the spectrahedron. So I'm a matrix, I live inside a spectrahedron, and I'm going to start walking toward the boundary and start leaving. Well, to leave the spectrahedron, I have to not have all positive eigenvalues. Right? One of them has to switch, which by the intermediate value theorem says that eventually one of my eigenvalues has to be 0. And so I'm going to be a singular matrix. And that's exactly why the algebraic boundary here is given by the determinant, because that tells you when the matrix is singular. As soon as I get on that boundary, I have a 0 eigenvalue. So maybe my sign is plus plus 0 here, the signs of the eigenvalues. And then when I leave, that 0 eigenvalue becomes negative. So I'm plus plus minus. And if I move through this surface again, but away from the spectrahedron, I might get a different sign change. So if I'm inside this cone region, I might be plus minus minus. And then if I'm on one of these sharp points, generically, I have 2 0 eigenvalues. Okay? So these sharp points are matrices of co-rank 2. In this case, that means rank 1. And they're exactly given by the XYZ values 1, 1, 1, and all of these, which I won't say out loud. So you can just do a sanity check for yourself. Let's see what happens if I plug 1, 1, 1 into this matrix. On the right-hand side, I get a matrix of all ones. And that is a matrix which has rank 1. So sure enough, that's a co-rank 2 matrix. So let me pause for any questions. And I cannot see the chat, so if there's a question in the chat, somebody please interrupt me.
So can I ask if the samosa in the middle,
yeah,
at least its boundary, there's no single algebraic equation that just gives that. You have to also get these cones on the outside as well.
That's precisely right, because the algebraic closure is the smallest one. So if there was, then the algebraic closure would just look like that. Exactly.
That's annoying.
Yeah, a bit, right?
Yeah.
But this is the same case for polyhedra too. You get these hyperplane arrangements instead.
So the picture you're drawing is still the real picture, right? And then you complexify. I mean, with this explanation of the intermediate value theorem, that was when the x, the y, and the z are real, and you're walking around that space, right?
Exactly.
Then you just kind of complexify because we always do, kind of thing.
Because we always, yeah, everything works so beautifully over the complex numbers. And if you're really
but if you
into
really
it,
want to think about the programming aspect, then you would want to keep real x, y, and z, right?
Yeah, yeah. With the application of semi-definite programming in mind, this lives in the world of real algebraic geometry. And yeah, I won't be drawing any complex three-dimensional varieties for you. It's all going to be real ones. That's all I can do so far. So yeah. Okay. So in this slide, I want to convince you that, well, these singular points themselves are solutions of polynomial equations, right? So if I have some hypersurface and I'm interested in the singular points, I ask that I find a point that's on the hypersurface and all the partial derivatives vanish at that point as well. So I can compute all of these singular points by solving a system of polynomial equations. Now, some of those solutions may be complex, some of those may be real, and we're mostly interested in the real ones, okay? And the thing that's going to be super, super important for the rest of the talk is that you think about this as a parameterized polynomial system. The data you're giving me are these matrices, A1, A2, and A3, and I'm spitting back out at you all of the singularities when I solve this system. It is a parameterized polynomial system where the data are triples of symmetric d by d matrices. Now, one reason we work over the complex numbers is because enumerative problems, like how many singular points are there, generically have a constant number, right? So if I ask how many real solutions are there to a quadratic polynomial in one variable, well, you'd say either 0, 1, or 2, right? Or none. Yeah, so 0. But over the complex numbers, it's always 2. When you count it with multiplicity. So that's one of the really nice things about working with the complex numbers. And so generically, there are d plus 1 choose 3 singular points on one of these symmetroids, and where d is the size of the matrices where we're looking at. So for d equals 3, this number is 4. For 4, it's 10. For 5, it's 20. For 6, it's 35. A lot of this talk will be focused on the 20 singular points of degree 5 spectrahedra. The question now is, how can these be arranged, right? So in the polyhedral setting, these singular points you want to think of as like kind of the vertices of these polytopes, which is a lot of combinatorial data about that object. And so we're trying to extract some combinatorial data here too, but we have to remember to work over the reals. And that brings us to the main definition of today, which is the combinatorial type of a spectrahedron. It's a pair of non-negative integers, rho and sigma, which counts, each of these numbers counts something. The first number counts how many real nodes are on the symmetroid. So on this whole picture I'm drawing, how many real ones can we see? The second one is telling me how many of those real nodes live on this convex body, the spectrahedron. Okay. So of course, rho is always going to be greater than or equal to sigma, because rho counts a superset of the thing that sigma counts. And this example is a quintic spectrahedron of combinatorial type 6, 0. There are 6 real singular points. You should be able to see 5 of them in this picture. I could not get a viewing angle where you could see all 6. So yeah, let's see, 1, 2, 3, 4, 5. and none of them are on the spectrahedron. The spectrahedron is completely smooth. Okay. So that's combinatorial type. And this is the main thing we're after. We want to understand the combinatorial types of spectrahedra. So what's known for small degrees? So for degree 3, it's known that cubic symmetroids have 4 nodes over the complex numbers. And you can either have all 4 of them be real and all 4 of those be on the spectrahedron, or you can have only 2 of those real and 2 of them would then have to be on the spectrahedron. Okay. In this case, the other 2 complex nodes are complex conjugate solutions to this polynomial system I described. For quartic symmetroids, this was done in 2010, first by Degtyarev and INTERMISSION, using something called the global Torelli theorem for K3 surfaces. These quartic symmetroids have 10 nodes, and there are 20 possible combinatorial types. And Degtyarev and INTERMISSION gave a complete description of what these pairs of numbers could possibly be. And some of these conditions are trivial, and we can see them immediately. So for example, this first one, since sigma and rho are counting something, they're never going to be negative numbers. As I mentioned before, rho has to be at least sigma. And then we're looking at generic things. And so rho will never be greater than the number of complex nodes, because rho counts how many real nodes are on the symmetroid, and real numbers are complex numbers in particular. The second one is that rho can't be 0. The third one is that sigma and rho both have to be even. Now, the fact that rho has to be even is very easy, because we already said that these singular points are the solutions of a real polynomial system. And so when you have solutions of a real polynomial system, the non-real solutions have to come in complex conjugate pairs. Okay, and so since there's an even number of solutions in total, and then you take off all the complex conjugate pairs, you have to have an even number of real ones left. The hard one is that sigma has to be even. So this was reproved by Adam Ronstadt, Strömfels, and Vincent in 2014. To show that these conditions are necessary, they use some beautiful classical algebraic geometry. And to show that they're sufficient, they simply give an example of each of these possible combinatorial types. There's 20 of them. So to prove to me that any of them can happen, you just give me one of each. Yeah. And so what we set out to do was to extend this result to Quintic Spectrahedra. And what we found is that there are analogous, very similar conditions which are necessary for any degree of a spectrahedra. And here they are. So the first one is completely as expected. They have to be non-negative. You can't have more real nodes than you have complex nodes, and rho has to be greater than or equal to sigma. The second one, again, comes from just the fact that non-real solutions come in complex conjugate pairs. It says that rho and the number of complex solutions have to have the same parity, meaning they're either both even or they're both odd. The third one says rho can be 0 if only if this funny number theoretic condition holds. D has to be -1, 0, or 1 mod 8. Okay. And then the fourth one is that sigma is even as well. So just to give a short description of how number 3 is shown, remember that these singular points correspond to matrices of corank 2. And one of these matrices in this space will have corank 2 or greater. Whenever we just look at the part not involving the identity, this has a repeated eigenvalue. You can imagine then if you have a repeated eigenvalue, take minus that eigenvalue times the identity, right? Yeah, and then that's something of corank at least 2. And then you just rescale so that the coefficient from the identity is 1. And it's already been proven that there exists such linear space as A prime, which consists entirely of matrices with no repeated eigenvalues, if and only if this number theoretic condition holds. And so we just rely on that to show number 3. And then number 4 is a little bit more complicated. And that's what I'll show next in a funny cartoon. So here's my funny cartoon. I'm in the case where I'm looking at Quintic Spectrahedra. And I'm going to look downstairs. This is supposed to describe my parameter space. So every point down here in this fun mosaic Picasso picture will correspond to some triple of 5x5 symmetry matrices over the reals. And then, as I mentioned before, as soon as you give me one of those, I can solve the problem, find 20 of them, 20 over the complex numbers, 20 singular points on the symmetroid. And the color coding up here is as follows. The gray points are non-real solutions. The red points are real solutions which are on the spectrahedron, and the blue points are real solutions which are not on the spectrahedron. So this 14 counts all the blue dots plus all the red dots, and this 6 just counts the red dots. And you can imagine, if I'm like a little ant on this picture, I can walk around and then see what's happening above me, see how these solutions move as I move around. And eventually, I'm going to find that I have some other combinatorial type. Some of these colors are going to change, right? And if you think about when this can happen, if I'm just walking over the real space, I'm always having these complex conjugate pairs. So if I'm going to get new real solutions, then that means the complex solutions have to approach the real axis. But then their conjugates do as well. And so you get a real point with multiplicity. And all the parameter values downstairs, which have a solution which has multiplicity, is described by these black curves. And these partition my parameter space into what are called chambers. And since this is the only way you can change how many real solutions there are, this is partitioning the combinatorial types, basically. So what's the argument that the number of red dots has to always be even? Well, the argument is that in order not the number of red dots is even, is if a red dot and a blue dot came together and then left as complex conjugate pairs through the space. And we're going to argue that the red dots and the blue dots never come together. Or more specifically, the places where they would come together are such small dimension that we can move throughout the chambers without ever having to worry about that locus. And that's basically it. So we start somewhere, we solve the system, and if we want to move to another chamber, we just randomly draw a little path somewhere else. And then the type, the combinatorial type, can only change when real points appear with multiplicity. That's when we get new or fewer real points. But then the number of red points changes if and only if one of these non-semidefinite, indefinite solutions collides with a definite semidefinite solution. But this is another application of intermediate value theorem, right? So we're in 5x5 matrices. Each one of these dots corresponds to a matrix with 2 zero eigenvalues. The red ones all have positive eigenvalues for their remaining 3. And then the blue ones have at least 1 negative eigenvalue. So in order for them to continuously meet each other, one of these negative eigenvalues is going to have to switch to be positive. And so that means that one's going to be 0 as well. So now we have 3 zero eigenvalues. And so we have a matrix of corank 3. So now you look at all the parameter values which have a solution of corank 3, and you see that the dimension is much, much, much smaller than the dimension of these black curves, and so you can always avoid it. So this never happens. That's the geometric argument for why sigma has to remain even. And this picture is going to make an appearance again in a moment. So here's our theorem that we had before for the necessary conditions specified for the case of d equals 5. So we just replaced the number before with 20 here. Rho and sigma are both even, and rho has to be greater than 0. And so there are 65 possible, a priori possible combinatorial types given this theorem. And they're listed here. They're just plotted. So rho is on the x-axis, sigma is on the y-axis here. And now the goal is to do exactly what Sternfels, Vincent, and all of them did to prove the other direction. We're just going to find an example of each. Okay. And so now we have a short intermission. So if you need to grab some water or some coffee, that's fine. I'm going to advertise one of my favorite tools, which is numerical algebraic geometry, to you. So numerical algebraic geometry, it's a computational paradigm for studying algebraic varieties using a computer. It contrasts itself with these computational tools, which are symbolic and exact. So computing Grosvenor bases, if you've heard of this, because it doesn't really focus on the algebra. It focuses a lot on the geometry, which has its perks and its setbacks as well. At the very core of numerical algebraic geometry, it can solve zero-dimensional polynomial systems really well. So maybe I want to intersect these two curves in the plane, and there are finitely many solutions. I will find them using numerical algebraic geometry by finding floating point approximations of them on a computer that are really close. And this is concerning to some mathematicians who like proving things sometimes because they're approximate solutions. So what does that even mean? How do you know if you've found them all? How do you know if they're right? And there are certification methods which can prove that your approximate solution corresponds to an actual solution. So a rigorous proof of this numerical calculation. And you can also rigorously prove when one of your approximate solutions that you found corresponds to a true real solution. Okay, so this is all about certification methods, which I talk about a little bit at the end. But other than zero-dimensional systems, it can study positive dimensional systems. All you do is you keep on slicing the variety until you have finitely many points. And then you use those points as a kind of a witness for the variety, and you can extract information about this positive dimensional stuff from these intersection points. You can compute irreducible decompositions, multiplicity of components, local dimensions, etc. If you know what these things are, great. If you don't, that's okay. And then one of the main benefits, in my experience, with using this instead of symbolic tools is that projections become easy. So if I have this twisted cubic curve here in 3 space and I want to project it down, it's very easy to do this from a geometric standpoint because projections are just linear maps. I would just take my approximate solutions, apply a linear map, and I get a representation of the projection of the variety. While with symbolic methods, you have to go through this Grosvenor basis or this elimination theory, and this can get costly, but it comes at the benefit of being exact. So it's just a different way to work with varieties, depending on whatever you need. And then the way I use these tools the most, so we have a picture like the one before, is by studying parameter spaces. So I have some parametrized polynomial system where for each parameter I have finitely many points. Numerical algebraic geometry allows me to literally perform analytic continuation on those points as I move downstairs. So every time you want to solve for a parameter, you don't have to do them independently. As soon as you solve for it once, if somebody gives you a different parameter that they want you to solve it for, you can just deform your solutions to those. And so this is very, very, very quick. And this is one of the main benefits. So they're super great for enumerative problems when you want to know how many points do this. So for example, for us, it's how many points are singular. You can understand what's happening when these points are colliding. You can still move to those. You just have to be a little bit careful. And for this talk, what's most important is that since we can solve many, many instances of these types of problems very fast, we can search for points with special properties, right? And so for us, we're searching for triples of symmetric matrices whose spectrahedra have a particular combinatorial type. Okay, so intermission's over. That's my advertisement for numerical algebraic geometry. So now I'll say how I used it. Well, the first idea is pretty naive, but it's not a bad idea. I'm just going to sample a bunch. I'm just going to pick a bunch of random 5x5 symmetric matrices over the reals, compute the solutions, these singular points, and then determine the combinatorial type and see which ones I find. And I use the software homotopy continuation.jl. This is software written in the Julia language. And I think probably in the course of a couple of weeks, I solved about 20 million instances of this problem by randomly choosing 20 million different triples of 5x5 real symmetric matrices. But the thing is, you don't find all of them this way. Okay, so I'm going to skip back for a moment. The reason why you don't find them all this way is because you have chambers like this, which are very, very, very small. So if I'm just randomly picking a bunch of points, there are chambers which have such small volume that you're probably never going to guess something in there. And so those chambers, which we couldn't find by just sampling, are listed in red. So these are the hard ones, these two corners of this triangle. So we had to do something a little bit smarter. And the smarter algorithm we used dates back to Dietmeier. And the idea in the case where you're just searching for how many real solutions there are, it's fairly simple and it's described on the left here. So here, let's say I have some certain number of real solutions of a univariate polynomial, let's say, okay? So this is supposed to be the complex plane, and here I have 1, 2, 3 negative solutions, 3 positive solutions, and 2 pairs of complex conjugates. And I'm going to start changing the coefficients of this univariate polynomial or something, and all of these points are going to move around. And as mentioned, we need complex conjugate solutions to come together and become real to get more real points. So that's what's happening as the arrow moves to the right, is that these 2 conjugate points are getting pushed together and becoming 2 real ones. Well, on the left, these two real points are getting pushed together to become complex conjugate. So what's the game here? The game is start somewhere in your parameter space, and if you want more real solutions, just pick a bunch of parameters nearby and see which parameters make the complex conjugate solutions get closer, and then repeat. And do this over and over and over again. And you hope that the computer does this and you find more real solutions. Or similarly, if you wanted fewer real solutions, you would just want to push together the real solutions so that they become complex, and you would just do the whole situation in reverse. But this isn't directly applicable to our problem, because we're not just interested about how many real solutions there are out of these 20. That's the row number. We also care about the sigma number. So we need a way to not just move to fewer real or more real solutions. We need a way to move in all 4 of these directions. One of these directions means picking up 2 extra spectrahedral solutions or losing 2 spectrahedral solutions. So that's I think that's the diagonals here. So this is gaining 2 spectrahedral, losing 2 spectrahedral. And to the right is gaining 2 singularities, which are indefinite matrices, and to the left is losing 2 of those, okay? And the game is pretty much the same. So in an analogy with this picture over here, so I've colored these blue and red suggestively. Again, it's just a cartoon, but the way I think about it is the blue and red here, is that these red points are positive, and these red points correspond to positive semi-definite singularities. So the idea, if I wanted to get more red dots in this picture, would be to push complex conjugate solutions whose real part is positive, and you push them together. So for us, that's going to correspond to choosing 2 of these gray points whose real part have a lot of positive eigenvalues and try to push them together. So this is just an adaptation of this old hill climbing algorithm, that's what these are called, to take into account this more refined structure of the real solutions, okay? And so we just do exactly that. We try to push together singularities with lots of positive eigenvalues on their real part, or not a lot on the real part if we wanted to go in the other direction. And doing this, we are successful, and we find all combinatorial types. And here is an example of a spectrahedron of each combinatorial type. So I'll take a moment on this picture. The top right corner, this is a picture of a spectrahedron of combinatorial type 2020. all 20 singularities are real. They all live on the spectrahedron. And as I move to the left, I still have 20 real singularities, but more and more of them are off the spectrahedron. And then all the way to the left, I have the spectrahedron has no singularities on it, and there are 20 real singularities off the spectrahedron. So this is the 20 real ones row. The next one is the 18 real singularities row. All the way at the bottom is only 2 real singularities. And you can see here, those 2 are not on the spectrahedron, and here these 2 are on the spectrahedron. Okay.
So each of these comes from a specific triple of 5 by 5 real symmetric matrices, right? So
that's exactly right.
And they all have integer coefficients. You can make them all integer coefficients, or
yeah. So with the numerics, we're always doing floating point approximations. Okay, and floating points, I mean, they are technically rational numbers represented on a computer, and so you could make them integer. You could try to find like a really close rational number for all these coordinates. And so we tried to find the simplest description of each of these. But again, for some of these chambers, they're so small, there's no nice, like small height rational number description of them that we could find. And so for like the 2020 case, for example.
So how big are these numbers? You know, does it make sense to ask for some kind of high? I mean, how big? You know, what sort of numbers are we talking here? I mean,
yeah, that question makes total sense, and we didn't rigorously do this.
Right. Okay. But each of these, I mean, you have some specific. No, I mean, you know, these are big numbers, or you know, it just doesn't. My question just doesn't make sense.
No, it totally makes sense. So I mean, I could just pick integers between like 1 and 5, and I'm going to get one of these. Right. So some of these have very, very small integer values as their coordinates.
Right.
But then some of these that we couldn't find unless doing this special hill climbing algorithm, these can be quite large, these heights. Does that answer your question?
Yeah, thanks.
Okay. Great. So I want to take a little bit of a closer look at 2 of these, the top 2 corners, because these were the hardest to find for us. And so here are different pictures of them. So the left one, you see all 20 singularities are real, they're marked in black, and none of them are on the spectrahedron, which is in blue. While on the right, all 20 are marked, and all of them are on the spectrahedron. And so these are really close, right? Like some of these singularities are super close. It's entirely unclear from the human eye that these are even like nodes, right? So what's really important now that we claim that we found all these is exactly to provide a proof, right? Because numerics aren't just going to cut it for free. But luckily, there are ways to certify, as I mentioned, that your approximations actually correspond to true solutions. And when your approximations actually correspond to real solutions, and you can also prove whether or not your approximations correspond to matrices which are positive or positive semi-definite. And I'm going to explain a little bit about how that works now. So what we use is something called Brysiewcz method. It uses interval arithmetic. So here, let's say I have some cubic univariate polynomial. Here are its roots. It's probably something like x cubed plus 1 or something, right? So -1's a root, and then these roots of unity flipped over the imaginary axis are. And let's say I have these red approximations of them. Now, in reality, these red approximations are going to be much, much, much closer to the true solutions. But for the sake of showing how this works, they're kind of far away. So the game is, you choose some box around all of your solutions, okay, that you found around all of your approximate solutions. And you do that in such a way that you definitely know that your approximate solution lives in that box. And then you apply Newton's method to this box. So Newton's method is going to always get you closer to roots, and it's the fixed points of the Newton operator are the roots. So you apply Newton's method to the box, and you cross your fingers and you hope that that box that you get as the image lives in the original box. Because as soon as you have this, you know that the Newton operator is contraction mapping. And so by a fixed point theorem, you have a fixed point in there. Okay, and by a stronger fixed point theorem, there's exactly one. And so what you get at the end is a certificate, which is a bounding box in each of the coordinates for its real value and its complex value, where you can be guaranteed that you have exactly one true solution in that box. And this is a mathematical proof. It is a certificate. And the way that you show something is real is you truncate your box. So that's fixed under complex conjugation. And then you apply Newton's method again. You see that it's still being contracted because solutions have to come in complex conjugate pairs. And then that shows something's real. And so, yeah, so you just keep contracting. And then in the limit, you get the true solution. Yeah, so this is just a repetition of what I just said. You get bounding boxes for where the true solutions live. You apply conjugation to see which ones are real. And then if you want to find, for example, the signature of the matrix corresponding to your true solution, well, you can do this by looking at what the values of the principal minors are. So this is like the image of your solution under some map, which takes your point to all the principal minors of this matrix. And you can apply that to the actual box too. And then you can check whether or not this is the image is positive and all of this, and it's still certified completely a mathematical proof. And so this is one way where you can actually use numerical algebraic geometry to prove something in pure math. Of course, you don't have to take it on faith that we did this. All of the code is available publicly online on the Max Planck Institute's Math Repo site. So there's code there for computing the combinatorial types of Quintic Spectrahedra, code for certifying these combinatorial types, these witnesses for each of the 65 types that I gave you in that triangle, and you get the cool images that I showed for all of those too. So I'm currently not pursuing this line of research in any of my current projects, but if you're interested, here are some questions I think are natural questions. So the first one, is there a more refined description of the combinatorics of spectrahedra? So for polyhedra, you don't just have what are the vertices or what are the faces or how many, but you also have how they meet each other. So an interesting thing would be to develop a reasonable definition for a more refined combinatorial structure in spectrahedra. What about three-dimensional or larger than three-dimensional spectrahedra? So I haven't looked at those at all. I'm not so sure if any work has been done on a notion of combinatorics of these things. So our conditions are necessary for all of these three-dimensional spectrahedra of any degree. But just as we had to find examples for the quintic case, you could try to find examples for the degree 6 case or higher, or even better, you could prove that these are all sufficient conditions for all degrees. And then finally, there's this idea of when a spectrahedron is not generic. So hiding in the background of all of this, I assumed some genericity assumptions on these this triple of matrices. Specifically that there were 20 complex singularities. Okay, of course, on this this boundary in the mosaic picture, some weird things can happen, and this happens all the time with polyhedra if you think about it. So it would be interesting to know not only what the generic combinatorial types are, which is what we did, but maybe all of them. So understand these very special spectrahedra as well. Okay, and that's my talk. Thank you very much for listening.